My name is Stephen Marsh, and I'll be your virtual guide in the greenhouse gas impacts of transportation fuels. We'll be talking about alternative fuel sources. Biofuels. In addition to the more traditional refined oil and gas products, such as gasoline, diesel, and natural gas, there are a number of fuels that are sourced from plant materials or organic sources. These include bioethanol, biodiesel, biomethane, and biohydrogen. As a group, these are all considered biofuels, which can be used independently or as blends with traditional fuels. Finally, both hydrogen and electric batteries offer regenerable energy carrying capacity. These differ from the aforementioned fuels in a subtle way. Hydrogen is produced industrially in one of two ways: steam reforming of natural gas or electrolytic separation of hydrogen from water, H2O. It is important to recognize that hydrogen gas deposits are basically non-existent on Earth. Thus, it takes energy to generate a fuel, which is in turn used to store energy. The same can be said of battery storage technologies. These are considered energy carriers rather than energy sources because we cannot mine or drill them from the Earth's crust. They must be created. Hydrogen has a great potential to reduce greenhouse gas emissions because it is an excellent energy carrier without any carbon in it whatsoever. Thus, it will not emit CO2 into the atmosphere. However, hydrogen production and delivery infrastructure has a long way to go before it can reach the maturity of competing technologies. Ethanol, bioethanol. Ethanol is known by many names and produced by many pathways. It is by far the most abundant biofuel produced globally, thanks to industrial fuel ethanol production from corn in the US and sugarcane in Brazil. Currently, ethanol is categorized as a first-generation biofuel. That is, a biofuel made from sugar, starch, vegetable oil, or animal fats using conventional technology. In fact, ethanol was among the first generation of transportation fuels in the US. Dating back to the early 1900s, it was one of two fuels available for the Ford Model T. A flex fuel vehicle, or FFV, is an alternative fuel vehicle with an internal combustion engine designed to run on more than one fuel, usually gasoline blended with an alcohol fuel, and both fuels are stored in the same common tank. Flexible fuel vehicles are designed to accept any proportion of the resulting blend in the combustion chamber, as fuel injection and spark timing are adjusted automatically according to the actual blend detected by electronic sensors. Today, ethanol is typically blended with gasoline in a ratio up to E85, that is, 85% ethanol and 15% gasoline. The popularity of several ethanol gasoline mixtures, including E10 and E85, has allowed vehicle manufacturers to optimize performance for these fuels. As mentioned previously, in the United States, the vast majority of fuel ethanol is derived from corn. The processing steps require fermentation of sugars, distillation, dehydration, and optionally a denaturing step, in which the ethanol is mixed with other chemicals to form an undrinkable mixture. Distillation and dehydration can be very energy-intensive processes, which developing technology seeks to minimize. The carbon intensity of ethanol combustion within the conventional pathway is 65 grams CO2e per megajoule. Additionally, there are new efforts underway to produce cellulosic or lignocellulosic ethanol, ethanol made from the woody structural parts of plants. This could lead to many changes in the industrial production of ethanol, because it drastically increases the number of available feedstocks, from stalks and husks to grasses and even wood shavings. A competing, but no less transformative technology seeks to use algae to produce ethanol from biomass. Developments in membrane technology to aid the energy-intensive ethanol water separation stage are expected to come within the next 12 to 20 years. According to a National Science Foundation and Department of Energy report, the key bottleneck for these advanced biofuels is the lack of technology for the efficient conversion of biomass into liquid fuels. Advantages of ethanol. According to the EPA, much of the increased interest in ethanol as a vehicle fuel is due to its ability to displace gasoline consumption from imported oil. As a renewable fuel source made from corn, E85 reduces life cycle greenhouse gas emissions, which include the energy required to grow and process corn into ethanol, by 15 to 20% as compared to gasoline. E85 made from cellulose can reduce emissions by around 70% as compared to gasoline. E85 can further reduce emissions of certain pollutants as compared to conventional gasoline and lower volume ethanol blends. For example, using E85 reduces carbon monoxide emissions and provides significant reductions in emissions of many harmful toxics, including benzene, a known human carcinogen. Not only does ethanol reduce emissions, but it can also reduce wear on engine parts. Blending biofuels with a petroleum-based fuel has the twin advantages that even relatively small percentage additions will result in a substantial total volume of gasoline substitution, and the present infrastructure for distributing fuels can be used largely unchanged. Recent studies have suggested that increasing ethanol ratios to 15% poses low risk of harm to the older cars still on the roads, those built from 1994 to 2000. Disadvantages. One of the major criticisms of ethanol as a fuel is the processing efficiency. Currently, the first-generation processes for the production of ethanol from corn use only a small part of the corn plant. The corn kernels are taken from the corn plant, and only the starch, which represents about 50% of the dry kernel mass, is transformed into ethanol. There have been numerous studies on the net energy balance of ethanol, which have suggested that producing a gallon of ethanol fuel requires more than 76,000 BTUs of energy, which, as a reminder, is the energy embodied in a gallon of ethanol. These studies typically consider food-grade ethanol as the processing pathway, and rarely account for current and alternative fuel manufacturing techniques. There is now consensus that there is a net positive energy balance for ethanol. Another associated criticism is that bioethanol necessarily diverts water, land, and grains from other uses. This is known as the food versus fuel debate. The contention is that any shortages caused by corn or sugarcane being converted into fuel will translate into increased grain prices throughout the world. These concerns may be lessened by the realization of lignocellulosic or algal ethanol technologies, but only time will tell. A practical disadvantage of ethanol is that the higher blends, E85 for example, have poor cold start characteristics. This is generally addressed by creating a winter blend, which, though still labeled E85, contains 75% ethanol. Finally, much of the ethanol market in the U.S. is supported by federal subsidies. This makes the issue of ethanol fuel inherently political and funding unpredictable. Biodiesel, renewable diesel, FAME. Biodiesel is a renewable first-generation biofuel, compatible with diesel engines. There are a few pathways to biodiesel creation, but the important takeaway point is that biodiesel is not actually a hydrocarbon, like diesel, but rather a fatty acid methyl ester, FAME, which includes oxygen within the molecule. This leads to some characteristic differences when compared to petroleum-based diesel. For example, like ethanol, biodiesel has some issues with cold start performance. The molecules may congeal within the fuel line. Thus, most biodiesel fuel conversion kits include either a small diesel startup tank or a fuel line and tank heater for use under cold start conditions. Like ethanol, biodiesel is typically blended into the traditional petroleum-based fuel, which leads to biodiesel blend nomenclature. B20, for example, is a blend of 20% biodiesel and 80% conventional diesel. Biodiesel can be processed from a number of feedstocks, including rapeseed and soybean oils, jatropha and other crops such as mustard, flax, sunflower, and palm oil, waste vegetable oil, animal fats including tallow, lard, yellow grease, chicken fat, fish oil, and even algae, which can be grown using waste materials such as sewage. For this reason, biodiesel has garnered a large following among the do-it-yourself crowd. Individuals can approach a restaurant and ask to pick up waste vegetable oil, which would otherwise be hauled off for a fee, and turn it into a fuel for their personal vehicles. Similarly, large-scale waste treatment operations are now recognizing an additional revenue opportunity by finding partners to source biodiesel purchasing contracts for diesel vehicle fleets. Biodiesel is the most prevalent biofuel in Europe, where diesel engines are more common. As such, there are many European vehicle manufacturers who are advancing engine technologies to handle biodiesel blends. Be mindful that biodiesel greenhouse gas emission intensities can vary widely based on the feedstock and processing pathway. They range from cooking oil and tallow with a CO2 intensity of 13 grams per megajoule to Brazilian soy which weighs in at 72 grams CO2 per megajoule. Renewable diesel. In addition to first-generation biodiesel, there are technological advancements which produce renewable or green diesel, long-chain hydrocarbons chemically identical to petroleum-based diesel, but created from recently living biomass. Renewable diesel shows promise as a drop-in replacement for conventional diesel with little to no modification to the fuel system necessary. Advantages of biodiesel. As with ethanol, the major advantage of biodiesel is the ability to reduce fossil fuel consumption through use of renewable, domestically produced fuel. Low biodiesel blends, B2 and B5 for example, typically require no modification to diesel engines and fuel systems to operate. Higher biodiesel blends, B20 and above, require only modest fuel system changes. Biodiesel is extremely easy to produce, to the point that individuals with little or no experience and expertise can get started on their own with a few tutorials. Biodiesel also has favorable viscosity and lubricity characteristics when compared to conventional diesel. Biodiesel is non-toxic and biodegradable and can reduce greenhouse gas emissions by 30% or more compared to petroleum-based diesel. Disadvantages. Although it is not usually detrimental to diesel engines, using homemade biodiesel can void some vehicle warranties. Because of the ease and distributed nature of production, some producers will adhere to quality standards more strictly than others. It is important to verify that any biodiesel purchased in the U.S. meets ASTM D6751-09A standards, or EN 14214 internationally. A drawback that biodiesel shares with ethanol is the food versus fuel debate. Common feedstocks for biodiesel in the U.S. are soy and rapeseed, also known as canola oil. Once again, first-generation biodiesel is not chemically identical to petroleum-based diesel, and first-time introduction may release built-up engine deposits, forming a surprising and embarrassing smog cloud. Electricity. Battery electric vehicles. An electric vehicle, EV, uses one or more electric motors for propulsion. Electric vehicles differ from fossil fuel-powered vehicles in that the electricity they consume can be generated from a wide range of sources, including fossil fuels, nuclear power, and renewable sources such as hydroelectricity, wind, solar, and geothermal power, or any combination of those. The electricity is typically stored on board the vehicle using a battery. Vehicles making use of engines working on the principle of combustion can usually only derive their energy from a single or a few sources. Electric vehicles were among the earliest automobiles, and before the preeminence of light, powerful internal combustion engines, electric automobiles held many vehicle, land speed, and distance records in the early 1900s. They were produced by Baker Electric, Columbia Electric, Detroit Electric, and others. At one point in history, electric vehicles outsold gasoline-powered vehicles. The current generation of electric vehicles in the United States dates to early 1990, when General Motors president introduced its EV concept two-seater, the Impact, at the Los Angeles Auto Show. The following September, the California Air Resources Board mandated major automaker sales of EVs in phases starting in 1998. From 1996 to 1998, GM produced 1,117 EV1s, 800 of which were made available through 3-year closed-end leases. Chrysler, Ford, GM, Honda, Nissan, and Toyota also produced limited numbers of EVs for California drivers. In 2003, upon the expiration of GM's EV1 leases, the entire EV1 fleet was dismantled and crushed. The politics of this decision is chronicled adeptly in the motion picture on the subject, entitled "Who Killed the Electric Car?" The film explores the roles of automobile manufacturers, oil industry, the U.S. government, batteries, hydrogen vehicles, and consumers, and their roles in limiting the deployment and adoption of electric vehicle technology. Honda, Nissan, and Toyota also repossessed and crushed most of their EVs, which, like the GM EV1s, these had been available only by closed-end lease. Although the operation of electric vehicles entails few direct emissions, all rely on energy created through electricity generation. Since electric vehicles use whatever electricity is delivered by their electrical utility or grid operator, electric vehicle emission calculations must take into account the carbon intensity of the generating source. Electric vehicle batteries. Batteries are usually the most expensive component of battery electric vehicles. Since the late 1990s, advances in battery technologies have been driven by demand for laptop computers and mobile phones, with consumer demand for more features, larger, brighter displays, and longer battery time, driving research and development in the field. The BEV marketplace has reaped the benefits of these advances. Electric vehicle batteries differ from starting, lighting, and ignition, or SLI, batteries because they are designed to give power over sustained periods of time. Deep cycle batteries are used instead of SLI batteries for these applications. Traction batteries must be designed with a high ampere-hour capacity. Batteries for electric vehicles are characterized by the relatively high power-to-weight ratio, energy-to-weight ratio, and energy density. Smaller, lighter batteries reduce the weight of the vehicle and improve its performance. Compared to fossil fuels, all current battery technologies have much lower specific energy, and this often impacts the maximum all-electric range of the vehicles.